All right, so 5035 MAA tutorial number 6. Guys, please, guys, eyes on me. We're going to solve question 3 of the recap tutorial sheet, which is about, remember, centroid of areas and the second moment of area. Do you remember what the centroid of a section is? And do you remember what the second moment of area is? The centroid of a section is the geometrical center of a shape. The geometrical center of a shape, you can imagine, it's the point upon which I can place the shape on the tip of my pencil, and it doesn't fall over. So it's the center of gravity, say, of that shape. So how do you find the centroid of a shape? It's very easy. It's just the weighted average. See here, for the centroid is the weighted average of the coordinates of the individual centroids of simpler shapes that make the area, weighted with the areas. This is also how we calculate your final grade for the modules. You have coursework is worth 40%, exam is worth 60%, then you do this. This is the weighted average, but that's what it is. Of course, why am I just using the y coordinate of the centroid? Why don't I need the x coordinate of the centroid in this case? For this particular case, what's going on here? Well, of course, this is a symmetric shape, and we know since it's the center of the shape, of course, the centroid must lie on any axis of symmetry. If you have two axes of symmetry, that's good, because where they intersect, there's the centroid. That's it. If you have only one axis of symmetry, you have to find, well, one coordinate is given by the axis of symmetry, and one coordinate you must find. So let's start by saying that this thing is symmetric. We say this is symmetric by doing this symbol here. And so that means that the centroid must lie on this axis here. But at which height? Where? Well, the other thing that we must start with is defining where's my origin. If I start counting from here, this is my 0, then I have some distance. But if I start counting from here, this is my 0, the distance is different. It depends. We want the coordinate of the centroid with respect to an origin. So let's say my origin is here. This is my origin O. So every coordinate will be measured starting from that point of that origin point O. Again, it doesn't matter which origin you choose. In the end, you will get the same point, but you will not necessarily get the same number. Okay? Because if you start counting from a different origin, the coordinate will be different, but we will all be pointing at the same point in the end. So let's do this. This is a complex shape. It's symmetric, but it's still not an easy shape because we don't know where the centroid is. Can we divide this into simpler shapes? I think so. I see very easily, I see two rectangles, one, there you go. And 2. But you can also be a bit more nuanced and divide this into other shapes. So I can say the large rectangle minus the smaller parts. Okay, that also works. But this divides the shape into 3 rectangles, which are more shapes than 2. So I would advise against this particular approach in this case. So I would say that this is rectangle 1. And I would say that this is called rectangle 2. And so let's apply the centroid formula. The y of the centroid, so the y coordinate of the centroid equals, in this case, this is a sum over i's. We have 2 shapes, so this is a sum of 2 members. A1, y1 plus A2, y2 divided by A1 plus A2. Do you agree with me? That's what it is. If you have three shapes, this gets more terms. Now, what is A1? A1 is the area of rectangle 1. What is A2 is the area of rectangle 2. What is Y1? What is Y1? It's the y coordinate of the centroid of rectangle 1. Now, do we know the centroid of rectangle 1? Of course, because we have split this shape into simpler shapes. Simpler meaning we already know where the centroid is. That's what is the meaning of simple. So in this case, the centroid of this rectangle is here. You might agree with me. Is in the center, of course. So this is the centroid of rectangle 1. Oh. And let me call this C1. And this is the centroid of rectangle 2. And let me call this C2. So what is the coordinate y1 of rectangle 1? The coordinate y1 of rectangle 1 is this here. Let's say I start from 0. This is my 0. I'll say this is the, there we go, this one. This one is the coordinate y1 I am looking for. Great. So starting from the origin towards the center 1, C1. All right? Good. And what is y2? Well, y2 is exactly the same. Well, this. Agreed? All right. Are these numbers or not? I think they are numbers because we can definitely calculate y1. That's 400 plus 25, 425. And we can calculate y2, which is just 200. Agreed? So y2 is 200 millimeters. Y1 is 425 millimeters. Okay. Let me call these ones, let me call this one capital B, 250 millimeter. Let me call this one T, which is the same as this. Let me call this 400 millimeters. Let me call this capital H. So because I don't want to use numbers, I want to use just formulae. So that means that YC is expanding this one, we get the area of rectangle 1 is capital B times T. So B times T, let me do this in capital BT, this is the area of rectangle 1, times Y1, which is a number. All of these are numbers. Plus the area of rectangle 2, which is capital H times T, times Y2, divided by the area of rectangle 1, which we just said is BT, plus the area of rectangle 2. And this one is the equation that you need. And these are all numbers. So in the end, you end up with 286.5 millimeters, which I'm just copying from this because I suppose this is correct. Can you please check if this is correct? If I made any mistakes? Anyone? Good, thank you. All right, And so we also discovered that whoever solved this question also used my same origin, because otherwise, we wouldn't know. And this is the answer. So let me say that the answer is in yellow. The answer is this one. This one is YC. Okay, which is where the centroid C is. This is the centroid C of the section. Okay, this part is easy. This part is what we've done in the first year as well. Remember this? And we didn't use it in the exam as well. Oops, but you are going to use it now. It's required. Second moment of area. Part B tells us determine the second moment of area about the x-axis passing through the centroid of the area. So we want to determine the centroidal second moment of area. Okay. How do we do that? Anything more? So the centroidal second moment of area is just, remember the second moment of area for simple shapes? So we also have that for this case, Ix, where x is this axis here, this is x, Ix is Ix of rectangle 1, let me do this in purple, Ix of rectangle 1 plus Ix of rectangle 2. It's exactly the same thing that we did for the centroid. Problem is that I for rectangle 1, we know that about this axis, x1, we know it's bh cubed divided by 12. Remember that? For rectangles, bh cubed divided by 12. For squares, for squares is L to the power of 4 divided by 12. And for circles, so for circular cross sections, you have pi d to the power of 4 divided by 64. That's how it was. Remember these? I'll put them down. You'll find these, as I was saying. You find these ones in a table. So this Ix comes from the integration of the y coordinate square. So the distance of every tiny element, of every infinitesimal element of area from the axis of interest squared integrated over the entire area. Now, of course, you don't have to solve the integral every time because we already solved these for simple shapes. You'll find them in tables, and I'm sure that Said showed you some tables with these already solved. So if you can divide your complex area into simpler areas of which you already know the second moment of area, that's good because we can just sum them up. Problem is, we can't really sum them up because they don't refer to the same axis. Say if I do this, Ix1, so for rectangle 1, bh cubed divided by 12, which is in this case b cubed divided by 12, this does not refer to this axis. Okay, this refers to this axis. And so we are already lost. So how do we make it refer to that axis? We use what we call the parallel axis theorem, which we also did last year. And it's about transforming a second moment of area, which we do know, into a second moment of area, which we don't know, as long as A and X are parallel to each other. As long as these two axes are parallel to each other, you can transform one into another by just adding this term here, which is the area times the distance between these two axes squared. Okay, so let's do that. So Ix1 is, let me split this into Ix1, 1 plus area 1, distance 1 squared, plus Ix2, 2 plus area 2, distance 2 squared. Distance 1 is this distance. D1 is this, is the distance between these two centroids. This is D1. And distance 2 is just this distance here. This distance. Agreed? The distance between the two centroids, basically. So, all right, let me split this equation once more time. I'm saying that this one, I know, this one is bh cubed divided by 12, and this one is bh cubed divided by 12, just a different b and different h for each. So this becomes b for rectangle 1 is just capital B, and h is t. So it's b t cubed divided by 12 plus the area of rectangle 1, which is bt, times the distance d1 squared. D1 is, as you can see, it's y1 minus yc. Do you agree? This distance here is this minus this. Everything is on the figure. This distance d1 is this minus this. So y1 minus yc. And remember, these are all numbers, because we found y1, we found yc, we know b, we know t, we know everything. Plus, this is also bh cubed divided by 12. In this case, b is t, and h is capital H. So it's t capital H cubed divided by 12 plus h times t, the area of rectangle 2, times, this is times the distance d2, and d2, you should agree with me that it's yc minus y2. yc minus y2, this is distance d2. Squared. Again, these are all numbers, so it should not surprise you that this gives you exactly the 658.7 times 10 to the power of 6 millimeters to the power of 4. Because remember, the units for second moment of area are millimeter to the power of 4. Mahmoud asking, we are trying to get the second moment of area of the shape around the x-line axis in the middle of the shape. Yes, that is the centroidal line, that is the centroidal axis. So we are trying to look at the I with respect to that x. That's it. And now that we know this, Ix, we can find any other axis. If I wanted to find the second moment of area about this axis here, how do I find out? Well, I know this. And so I just do that plus the area of this entire thing times the distance squared. But that's out of scope, because these are the two results we were interested in. Okay, how easy is this? I think pretty easy. Right? Good? Good. All right, let's go a bit more in depth with question 5 of the tutorial. Always recap tutorials. So these things is still a thing that you should remember from last year. We have this beam, constraint, point load, and we have distributed load of 3 kilonewtons per meter, point load of 4,200 newtons, 2 reaction forces that are already calculated, and a cross-sectional area that looks like that, which we already found. Now, for the cross-sectional area, as you can see, we already have the position of the centroid, which is 99.6 millimeters from the bottom or 60.4 millimeters from the top. And you have to remember how to find the reaction forces. This is very easy. Now, this is pin joint in A, roller in B, and you have this one and this one. This might have been easily question 1 at the exam for 4025 MAA. If I wanted to be a bit nasty, probably I would give you this one as a question in exam, at the exam. I was very generous at the exam. All right. So we know how to find the reaction forces. In fact, we are not even required to find the reaction forces. They are already here. So we want to sketch the shear force diagram for the beam showing significant values, and sketch the bending moment diagram for the beam showing significant values. All right, how do we do this? We also want to find the maximum tensile stress and the maximum compressive stress in the beam due to the bending and where they occur. So which point in this beam is the most stressed point? That's what I'm asking in bending. All right, how do you do that? How many segments you need to study this beam in? Three, okay. Let's say segment 1 goes from 0 to 2. So this is segment 1. Segment 2 goes from 2 to 7. Okay, so this is segment 2. Segment 3 goes from 7 to 10. So we need three cuts, basically, because we need to study this in 3 segments, and then we have to stitch up the solution at the end. All right, so let's start with segment 1. Do I look left or do I look right? Which one's easier? Right. Who said right? Why? Is that easier? I don't think it's easier. Right. If you look right, you got all these things. If you look left, you only have this. I mean, it's not wrong. But you're being a masochist. Do you remember what I'm doing here? Do you know what this is?
Sign convention?
Yeah, correct. Thank you. Sign convention. Remember, this is the Santini. Always bring it with you. Remember this is always the sign convention for internal forces. We want to find the shear force diagram and the bending moment diagram. So I'll start with segment 1. You know what? Let's see if I can do this properly by splitting this thing into this page into three sections, since we need 3 segments. And so this is segment 1, this is segment 2, this is segment 3. Segment 1, x goes from 0 to 2 meters. Segment 2, x goes from 2 meters to 7 meters. Segment 3, x goes from 7 meters to 10 meters. Okay? This is the proper way of doing it. And so for this one, I'm looking left. For this one, I will look, probably look right for this. Yeah, look right. And for the last one, I'll definitely look right. Okay, and again, it doesn't matter if you look left or right, the internal forces are the same because they're equal and opposite to each other, no matter which segment you take. All right, so let's look left on here. I have, this is the beam. And I know that there is a force here of 4,200 newtons. And I know that this is the cut. And I know that this is the convention, says that M of x looks like this, and V of x looks like this. And this distance, of course, is x. That goes from 0 to 2 meters. All right, if I do the free body diagram of this side, of this one, I get, looking right, I get all these things. This is the cut. And I have here 3,3637. Let's call this BY, okay? Let's call this BY. This is a number that we know is this one. And then we have the 3 kilonewton meters load. That goes from here to here, say. So we also have a part of the distributed load. So how long is this beam? How long is this chunk that is left?
You mean the last one?
I mean this. How long is this chunk? What's this distance?
5 minus x. 8 minus x.
How long is this? Guys, look at this. I am drawing this part. Okay, so how long is this part? Given that this is x. This is x. 10 minus x. Oh, there you go. 10 minus x. Thank you very much. Ten minus x. Also, what's this one? Because this is also important. See, I'm cutting here again. How long is this? 5 minus x, 7 minus x. What do you think? I cut in the middle. Well, no, it doesn't matter. Mahmoud, it doesn't matter where you cut. As long as it's in between in between 2 and 7, it's fine. So Saim says 7 minus x, and I do tend to agree with him. So yeah, let's say this is 7. No, let's not say this is 7 minus x, okay? Because this is what's going on here. This is 7 meters minus x. This is x. 7 meters minus x. This is what's left. All right, that's it. No way around it. Okay. And finally, the last free body diagram. This is the cut. We still have by here. We don't have the distributed load anymore. So I'm just drawing this side, this part, so I only have that force. And so what's the length? What's the length? Ten minus x. Okay, always 10 minus x. It's now that x is larger. That's why it's shorter. And we still have the same bending moment and shear force as per convention. Agreed? These are the 3 free body diagrams. And now we do equilibrium equations. Now we do equilibrium equations. That means that for equilibrium, I have, sorry, let me do this. Minus 4200 minus v of x equals 0. Agreed? That's what happens here. And for the bending moment, I have 4200 times x plus m of x equals 0. Do you agree with me? So these are the equations. And if I solve the equations for v of x and m of x, I get that v of x is minus 4200 newtons, constant. And m of x is minus 4200 x, linear. Remember, this is the equation of a straight line. Is there a way we can check if this is correct? Is there?
If we differentiate,
yes.
we should get the
So if you differentiate, remember, this is always true. The derivative of the bending moment with respect to x is the shear force. Okay? Always, always. So if we take the derivative of minus 4200x with respect to x, you get minus 4200. That means we are correct. So let's do the same for segment 2, which is much more complicated.
Sure.
Yes?
The derivation, what was it equal to?
V of x.
V of x.
So let's do this for the shear force. For the shear force, we have V of x minus, remember, this is the equivalent load, F equivalent. How much is F equivalent? 3 times 7 minus x. Agreed? Minus 3 times 7 minus x plus by equals 0. This is the equation. And for the moment, we have that minus m of x, this one. And then we have this one is also negative because it's clockwise. It's F equivalent. So minus 3 times 7 minus x times this distance, which is 7 minus x divided by 2. So squared divided by 2 plus by times 10 minus x equals 0. This is much more complicated, of course. Agreed? Now, while I rewrite v of x, you calculate m of x, and you let me know in the end what's the expanded. Let's do this expansion. Well, you do it, because I'm busy doing v of x. I'll do v of x, you do m of x. So v of x equals minus 3x plus 21,000 plus by, which was 3,637. 3,000.
In Tokyo, Japan,
637. Lynn, can you please check if this is correct? Should be correct.
Yeah, I'll take a calculator.
Yeah, or you can just look at the solutions. I think it should be inside. I don't have them handy. Let me see.
Let me see.
Because if we screw up now, it's going to be a mess. And help me out here. Of course, this is the equation of a straight line. So I am expecting that the integration of this gives me a parabola. Give me a parabolic function. So I'm expecting something. So of course I'm expecting here minus 3/2 x squared plus 24,637.5 x plus something. That something must be the constant of integration, which I don't know, but I can find out because I know that the moment here is 0. Oh. I know that the moment here is, no, it's non-zero. No, the moment there is non-zero, so it's not easy. It's not easy to find. Okay. Come on, I've done this for you. What's that number? What's that number? Have you done it?
24,366.
Yeah, 24,637, which comes from 21,000 plus by, and by is 3,637.5. Okay.
Thank you.
Yeah. Is it not? Oh, because it's negative. Yes, thank you. It's correct. So this is not 24,000 because it's 21,000 minus 3,637, which is 11,000. What? Let me see. Solution. There we go. This is it. 11,362. Apparently it's 11,362. No, it's not 11,000. How can it be 11,000? 11,000 is V of x here. V of 2 is 11,000. But this one is I think it's this. Come on, let me out. Let me fire up my calculator, and I have this should be 21,000. Oh, it's minus 21,000 minus this. It's minus 3x for sure. Plus 21,000 minus by. Okay, so 21,000, 1,000 minus 3637.5 is 17,362.5. 17,362.5. So this is, of course, the same. 17,362.5x. And did you find out what's this? Did you find out what's this number here? Come on. It comes from this one and this one. How hard can it be? How hard can it be? How can you spend so much time on a simple calculation? Come on. You are lucky that for this semester, the exams are still online. Next semester, they will be physical on campus. And you have 2 hours. If you spend 1 hour on a calculation, that's not good. Okay? I might even consider giving you a break after this, if you deserve it. But so far you don't.
Your largest knows no math.
No, I know. Guys, really? Or from Alpha, help me out. You're my only hope. So we have minus 3 times 7 minus x squared divided by 2 plus 3,637.5 times 10 minus x. There you go. Is there an expanded form? There you go. This one. Guys, was it too hard? I don't think it was too hard. Minus 3 halves there, minus 3,000. Oh, of course, this is also not. How is it possible? Minus 3,000. Did I mess up? Minus 3, 7 minus x squared divided by 2. Yeah. Plus this. Is there anything else I missed?
The 3 is probably
The 3 is here. Oh, 3 is correct. Minus 3 plus this. Okay. So let me check this one then. This 0, v of x. Oh, sorry, not this. Oh, so it was incorrect. It wasn't 17,000. Okay, so in the end I get 3,616.5. And so in the end, this one is minus 3/2 x squared minus 3616. No, this is minus plus or minus. Oh. (3616.5) x plus 36,301.5. Okay, so this is how it looks like. And the last one is, and now this one is easier, v of x plus by equals 0. And this one is minus m of x plus by times 10 minus x equals 0. And so if I do this, I get that v of x is minus 3,635, not 37, 3,637.5. 7.5 newtons constant, and m of x is 36,000. It's minus 3637.5 x plus 36,375. And this is a linear. Okay. So let's find out the actual thing. So if I start from here, and this is my x in meters, and this is my v of x in newtons, and this is also my m of x in Newton meters. I end up with, this is minus 4,200. Now this is of course from 0 to 2 meters. This until here is 7 meters. And until here, this is 10 meters. I'll remove this one because this is easier, so we are not going to solve this question because it's more of the same. And now let's say v of x is minus 4,200 constant, so it goes here. And this is minus 4,200. Then we have, this is a line, so we want v of 2 and v of, so this is negative, should be negative as well. Yes, because otherwise this is not the derivative. So minus 3 times 2 is minus 6,000. So this is minus 3,000. Guys, help me out. Help me out because we have to use the correct units. These are newtons. And so these must be newtons as well. And this is also 3,000. All right. Because this one was kilonewton meters. So this one really should be 3,000 newtons per meter. And this is 3,000 here and here. Okay. So according to this, we have minus 3000x. Let me do in Wolfram alpha. So minus 3000x. Minus 3000x. Minus 3616.5. Sorry, where x equals 2. We get minus the rational 4 result minus 9,616. Is it? No? Is it correct or not? $11,000. How is this possible? So this should be a jump up. So this one should jump up. So this is correct. And there's a jump up of 15,000. So what did we miss up in this? And what did we mess up? Let's say. So we have V of x is this. Minus 3000 times 7 minus x. Is this 7 minus x? Oh, that's why. That's why. No, it is 7 minus x. This is 7 minus x. This is what's left. Okay, so this is correct. This is 7 minus x. This is 3 more. It's 10 minus x. Correct. And the distance is minus 3000 times 7 minus x plus by. So let me do this in Wolfram alpha again, or probably because last time in Wolfram alpha I didn't use this. So we have V of x minus, so say plus 3000 times 7 minus x, 7 minus x, plus, sorry, negative, minus by, which was 35616.5, 3637. What? 637. All right, so minus 3000 times 70. Oh, I was right. It was 17,000. Why did you tell me it wasn't? 17,362.5. And for this one, if I do this squared divided by 2, and I add, so this is square, this is negative, this divided by 2, and plus by times 10 minus x, I get this thing, which is minus, see, 17,000, it's the same, was correct. It's minus 17,362.5 plus minus 37,135. 37,125. Okay. So if I do this now, if I look at the previous one, and I say that x equals 2, so V of x is this, minus 3000x x plus 17,362.5, where x equals 2. I get 11,000. 11,362. So start from here, say, is 11,362. And then I need what's happening at 7, because I need another point here. So what's happening at 7? Let's get it. Let's check it out. At 7, it's minus 3,637. Of course, it must be. So if I go here, and I end up, say, here, this is where I end up. And then, of course, this is constant. It's constant by exactly the same number that we found here, which is minus 363, minus 3637.5 newtons. Okay. So that means this is negative, positive, negative, negative. And of course, this point is also interesting. How do we find that point? You put Vx equal to 0. So you put Vx equal to 0. This one. So we are in segment 2. So we take this Vx, we put it equal to 0, and we find out where is x. So minus 3000 x plus 17,362.5 equals 0. That means that x equals 17,362.5 divided by 3000, which is equal to, if I do this, I can find out where this is 0. Equals 0. And this is 0 at 5.78. So this is 0 at 5.78. Finally, for the bending moment, it's linear. So minus 4200x, that means when x is 0, I start from here. When x is 2, it's minus 8400. So say from here to here. This is minus 8400 Newton meters, of course. And then we have a parabola. A parabola, we need 3 points for the parabola. Remember that? That means the starting point, which of course, since we have no concentrated moment, it must start from here. An ending point, which might be good if we find it from here. So minus 3. Let's do segment 3 first. We've done segment 1. Let's do segment 3, because then we can just connect it up in the middle. So for segment 3, let me do this. When m of 7 and m of 10. M of 10 is 0, of course. So I know that I must end up here, because minus this times 10 plus this, it's exactly 0. But at 7, this is minus 3637.5 times 7 plus 3637.5. No, sorry, not this. It's this. This gives me 10,912. So it gives me 10,000, so more or less the same. So 268,9. So let's do here. 268,9. So here. So this is 10,912. 10,912.5. And I know that this parabola must start here, end here, and has a maximum in the middle. Has a maximum here. How do I know that the maximum of the parabola is here? How do I know? Correct. It must be because, remember, derivative of the bending moment in the x is the shear force. And so that means that where the shear force is 0, we have a critical point in the bending moment. So it's either maximum or minimum. Do you agree? Does this look like what you have in the solution? I think so. So this is negative. Here becomes positive, positive, positive. What does it mean for the bending moment to be negative? The beam is frowning. The bending moment positive, the beam is smiling. That means the beam is frowning until here. So this is another important point. How do we find this important point? This important point here, you put this thing equal to 0. Okay, so let me put this in Wolfram alpha and let's find where is this 0. So minus 3000, I think it's this one. Okay, so this is minus 3000 minus minus 3000 plus by times 10 minus x, okay, equals 0. And let's find out where is this 0. This is 0 at 2.83. So 2.83. So this point here is 2.83. And we know that the beam is frowning until 2.83 and then starts smiling. So if we look at this deflected shape, we said it's frowning until 2.83. So after this point, so this is still frowning. And then it starts smiling. Okay, so this is the deformed shape of this beam. Frowning until 2.83, say here, where it has this inflection point where it starts smiling again. Agreed? Again, this is not hard, it's just laborious because you have to make things good. And you see, it's not very easy, especially if you are in a rush like me in a tutorial session to solve this. So you have to practice. Of course, this is first year stuff. So you are not probably required to do this once more at the exam. Okay, there might be some elements of this that you need to do because it's required, but everything should be okay. Any questions? No? I think that now you deserve a break. Okay, so I'll give you 5 minutes break. And let me check any questions online. Marius, yes, you were correct. 3,000 times 7. Unfortunately, I haven't looked at this earlier.
How do you see the moment? So you see this one. How do you always know this 7 minus x squared all over 2?
Because this is this force, which is 3,000 times 7 minus x,
It's the square root of 2.
at the distance, applied at the distance, which is this distance here, is 7 minus x divided by 2. You agree that this distance here, this is 7 minus x, this is half of this. Okay, so if you do this times this, you get 7 minus x squared divided by 2.
Okay.
Yeah.
Does that say 10,100?
10,912.5. But
Okay.
it's the same that's in the solutions. If you look at the solution. Yep.
So I had the same issue last year, so So how would see when you cut it? Yeah, how would you always know what direction the makes the shear force?
Yes.
You could do this VF could is that like a reference?
Yeah.
A reference.
This is always the case. If you look left, if you look left, use these.
So say that again. So if
If you look left, use these. See, I'm using this. And if you look right, use these. Always.
If you look left,
use the ones on the right.
and if you look right,
Use the ones on the left. Because the forces exposed are exposed on the left.
oh,
Okay.
Yeah. Is it paused? Good question. Yep. Well, probably should have got this ready before. Basically, I teach as well. Right? Do you know you've got one note and everything open? Do you know how you draw arrows and it'll turn to arrows? How do you set that up?
Don't have one.
What's this? What's this?
This is not ability.
Huh?
Not ability.
Oh, so it's not one note. Okay. Is that just free?
I think it's 9.
Oh, and that's it. And where'd you get it?
On the App Store.
It's in the App Store. What was it worth getting? No, to the. Cool. Cheers.
Okay, so let's resume. I just noticed that we didn't answer the question. It says calculate the maximum tensile stress. Okay, so we ended up calculating the largest bending moment, which is, I'll just use the largest bending moment is is there a maximum here? Maximum this. The largest bending moment. Where's the maximum point? Maximum. Somewhere. Max. Okay. Come on. There you go. So at 5.78, as I said, the maximum is 13,170. 13,117.7 Newton meters. That's the largest bending moment. That means the beam will break at 5.78 meters away from the start of the beam, because that's where the largest maximum moment is. That means you also have the largest stress. Now, where is the stress? Where is the largest stress? As you might remember from first year, let me move this here. The largest stress, largest bending stress occurs if this is the neutral axis. So this is the neutral axis. So that means that the largest stress, there you go. As you can see, it must occur here. Let me do it on the other way around. No. There you go. Yeah. Oh, I had work. Yeah, everything is fine. Thank you. Okay, so as you can see, this is the neutral axis. Let me do this like this. And we know that the stress is negative here, so sigma negative compression. And well, let's just call it sigma compression at the top fiber of the beam. and we have sigma tension at the bottom of the beam. Agreed? So which one of these is largest? Of course, the bottom one. Maximum tensile stress occurs at the bottom of the beam. And how large is this? How do you calculate the tensile stress in bending? Very simple. Sigma equals minus m over I times y max. So this is sigma m over I times y, but sigma max, of course, is y max. Where y max is the largest distance, the largest perpendicular distance from the neutral axis, which in this case is exactly 99.6 millimeters. And I is also given. You don't have to calculate this. I is given. So this is called IZ. So let's use IZ in our formula. And let's call this Y max. And so this is IZ. And of course, we have M max. M max is this one. Largest moment divided by IZ times Y max. These are all numbers. And this gives a number that is, according to the solution, 188.6 megapascals, Newton per millimeter squared. 188.6 megapascals. And this is the final answer. All right, now let's do, yes, what's the question? There's a minus because it depends on the moment. If the moment goes this way, then it's compressive at the top and tensile at the bottom. If the moment goes this way, it's tensile at the top and compressive at the bottom. If you're bending with a positive moment means compressive at the top. So negative at the top, positive at the bottom. So that's why you need a minus sign. Okay? It's just a minus sign to tell you which ways, because you have your y-axis also goes up or down. So it depends if you use negative y or positive y. It depends on how you orient the axis generally. So don't worry too much about it. You know what's going on. If the beam is bending in one way, so you have compression at the top and tensile at the bottom. And if it's bending the other way, it's tensile at the top, compressive at the bottom. Let me check the questions. Okay. No, the third segment should be, this should be correct. This is definitely correct. Okay, let's do direct shear. Direct shear is, remember when we said that in first year, we said that if we have a section of a beam, and this section is under the influence of a normal force, this normal force comes from a constant distribution of stresses, sigma, which we say is N divided by A. Agreed? That's what we have. And that's always true. That's always exact. We also said in first year that if we have the same thing for a shear force, we could, on average, if this is the shear force V, which of course is not perpendicular, is parallel to the plane, parallel to the cut, we can say in principle that there are the same tiny pressures applied in the same direction, and they are on average, tau average, V divided by A. Remember this? This is what we did lecture 6 last year. I know it's lecture 6 because it's week 6 and I'm doing this exactly the same for your colleagues of the first year. Okay? Now, this thing on average is true. On average, all these arrows have the same length. And that length is V divided by A. Force over area, that's a pressure, that's a stress. Shear stress. Shear stress because it's parallel to the cut instead of being perpendicular to the cut. All right? All right. Now, you are in second year now. So the average shear stress is not enough because we want to know what's happening exactly at every point of the section. And so you have learned in this lecture with Said that the shear stress is not distributed constantly over the area. The shear stress is distributed parabolically over the area. That means the arrows here are 0. And the arrows grow and grow and grow until they reach the centroid of the section, where they are the largest. And then they start decreasing until they reach 0 again at the other face. All right? And this parabola is encoded inside this equation. Do you know about this equation? VQ over IT? Okay, good. Now, V is the shear force. Easy. This is the sum of all these tiny arrows gives you V. I is the second moment of area. That's established. What is T? What is T? T is the thickness of what? T is the thickness of the cross section at a point of interest. This is T. Let's say I'm interested in finding what is the arrow here at point A. The arrow associated with point A is not the largest, is one of the largest. See, it's this one here. It's in that direction, and the thickness associated is T of A. So it's the thickness of the section where the point of interest is, which in this case for a rectangular section is all the same, it's just T constant, but for some sections it might not be the same. If you have a section like this, T A and TB are not the same. This is TA, this is TB. Okay, they are not the same thickness. So you have to take into account what is the thickness at the point of interest when you calculate the stress at a point. Okay. So what is Q? Now Q is a completely different thing. Q is the first moment of area of the shaded area. What is the shaded area? The shaded area is the line that we use to find the thickness. We can shade the top or the bottom. And that Q is the first moment of the shaded area, which is either the top area or the bottom area. Again, it doesn't matter which one you take. Sometimes it's easier to take the top one. Sometimes it's easier to take the bottom one. And this, inside this Q, there is the parabolic magic, which you don't see here. It doesn't look like there's any square. So how come this is parabolic? The square comes inside this AS times Y. Because AS depends on Y, so it's Y squared. So that's where the parabola comes from. All right? All right. So let's now solve this problem, for which we have a symmetrical I section subjected to a vertical shear force of magnitude 200,000 newtons. And the line of action coincides with the center line of the web of the section. So that means we have a very large shear force applied here in the middle, V, exactly in the middle of the section. Determine the value of the shear stress in the web at its junction with the flange. Do you know what is the difference between flange and web? So for cross sections, everything that is horizontal is called a flange, and everything that is vertical is called a web. Why do we need these things? I mean, why don't we have just a rectangular area? Because since the stress, look at the distribution of normal stress in bending. In bending, the stress is concentrated far away. Do you agree? So ideally, I only need the material far away from the centroid. And that means I don't need a thick web. I need a thin web. If the beam is only to be loaded in bending, the material needs to only exist far away from the centroid, because that's where the material is required to resist the stress. That's why we have thick flanges and thin webs. That only if you're using the beam for bending. Because if you're using it for any other thing, the thin web might cause issues. Right? All right. Okay, so let's redraw this one, because I have to mess up the drawing a bit. I'm gonna make it much larger than it is. Okay. First of all, this looks to me, how many axes of symmetry we have here? Two. Oh, so do we need to find the centroid? Well, we need to find it, but it's easy. Okay, so where is the centroid? In the middle. So this is the first axis of symmetry. This is the second. 1, 2, 3, 4, 5, 6, 7. Of course, of course. There you go. Okay. So this is my second axis of symmetry. 1, 2. This one. I'm going to use to mark. I'm using this to mark the centroid. And I'm using it to draw this other symmetry symbol. So this is the centroid. Agree with me? Should be no question about it, because we have two axes of symmetry and they intersect in that point, so the centroid must be at that point. What else? What do we know? We know that this is 14, so the thickness is 14. Let's call this T. Which is the same over the entire thing. Oh no, the flange is shorter. Let's call this T of the flange and T of the web. And then we have 125. I'll call this capital B. And I'll call this entire thing is capital H. Okay. Let me bring this a bit to the right. Okay, so how do we calculate the shear stress? Let me use the equation again. The equation is tau is V times Q divided by I times T. Okay, what is I? Well, let's say that we can calculate I. I is easy to calculate. That's left to you as an exercise to calculate I of this section here. We want, well, V is given, V is 200,000 newtons. So this is 200 kilonewtons. I, you can calculate, this is a number in millimeters to the power of 4. What is T? Well, we want T, the value of the shear stress in the web at the junction. So I want to find the stress at this point A. How do I find the shear stress at this point A? What is T associated here? It looks like we have two T's. If I come from the top, it's TF. If I come from the bottom, it's TW. Agreed? Thickness of the flange if I come from the top, thickness of the web. So that means we have a discontinuity. Discontinuity of the first kind. Because as we go down, we jump from TF to TW. That's quite a large jump. We go from very large to very tiny. We go from 125 to 9. That's the jump. So the shear stress, look at the formula. The shear stress, does it increase or decrease when I go down? Does it jump down or jump up? Of course, increases because T is at the denominator. So the stress, which is small, at some point, boom, shoots up, the shear stress. And then it keeps increasing because it's parabolic. So what we have is a parabola, because this Q gives you a parabola that is broken in 3 parts. There is a parabola from here to here, then jumps, a parabola from here to here, then jumps down, of course, then a parabola from here to here. Do you agree with me? So this is the same parabola that is broken in 3 parts because we have 2 jumps in thickness. There is no jump in Q. Q is continuous, but T is discontinuous. T jumps. This one is the continuation of this parabola, but we have broken it because there is a jump in thickness. So let's do this calculation. We need to find Q. What is Q? The first moment of the shaded area. Okay, what's the shaded area? This is T. So this is where I want to find the stress. So the shaded area is either the top area or the bottom area. Which one is easier? The top area. Huh? It's already a rectangle. And also the first moment of the shaded area, we also need to find the centroid of the shaded area. And the centroid of the top area is much easier than the centroid of the bottom area. The centroid of the bottom area is basically question 1 that we did in the recap today. So the centroid of this area is this one. Did I screw up again here? Yes, I did. Let me. There you go. So I can point out better where is the center. This is the centroid of the shaded area. I'll call it CS. And this is the shaded area. Shaded area. Call this shaded area, AS. That's CS, is the centroid of the shaded area. So what do we want to find is Q is AS times Y bar. What is Y bar? Did Said tell you about Y bar? Of course he did. What is Y bar?
Centroid. The Y.
The Y.
Coordinate of the centroid.
No, almost, but no. It's not the Y coordinate of the centroid of the shaded area. Y bar is the distance between the centroid of the shaded area and the centroid of the section. Agreed?
Yeah.
Y bar is YC minus YCS. Okay, and this is not, let's use it as a absolute value of YC minus YCS, because it doesn't matter where you start counting from, even if it's negative, it's still positive. So Y bar is this distance here. Let me do this in, let's use yellow. Y bar is this distance. Okay? How much is that distance? Well, looks to me it's h minus, so h divided by 2 minus tf divided by 2. You agree? Do you agree? Ah. So this is h divided by 2 minus tf divided by 2, which I can also call it as h minus tf all divided by 2. These are all numbers. I just don't like using numbers because I might miss some important information. So this is y bar, and that's it. So we can just substitute numbers here. What's the shaded area? AS is TF times B. So capital B times TF. And these are also numbers. So overall, I get that tau is equal to V times BTF times y bar divided by I times T. And this T is either TF or TW, depending on if you're looking on one side or the other side. Because at A, what you have at A is this thing here. So if I draw the shear stress diagram, this is tau. Tau starts at 0 here, and it must end at 0 here. How do I know? Well, I'll show you now that y bar, I'll show you now. Start from 0, take my word for now, and then goes here as a parabola. Not like this though. Come on. Help me out. There you go. And then it shoots up. Let me put this here. And it shoots up. Then he has another parabola here. This is duplicate. And it shoots up here again. And this one goes like this. This one is, of course, start like this because this is not true. And as you can see, TA, at point A, you have two shear stresses. You can calculate this one if you use the largest one, so TF. No, the largest one is, sorry, this is not TFW, because this is either B, capital B, if you're looking from the left, this is T minus, tau minus. And if you're looking from the right, it's the same. So tau plus is the same, but you are using TW. Okay, so this is, by using B, you get this. And by using TW, you get this. At the same point. That's what's going on. At the same point, you have two stresses. One, if you come from one side, you get this, which is a number. And that number is, let me find the solutions. That, not this one, not this one, not this one. Which question is this? Question 3. Question 3. Question 3, there you go. 64.1 megapascals. This is using, no, this is using lye. So this is TW, 64.1 megapascal. And using the other one is, no, it doesn't say. You can find out. Apparently, it just finds the largest one on the shear. So it finds this one. So this one you can find by using B in the formula. And of course, the largest one, the absolute largest one, is at the centroid. How do you find the one at the centroid? It's the same thing. You just have to recalculate the shaded area, of course, and recalculate the thickness. The thickness is TW, because at the centroid, the thickness at the center is TW. But the shaded area is now this one. And it doesn't matter if you take the top one or the bottom one, is always the same. Problem is, Y bar is also different now, because you have to calculate the centroid of the shaded area. The centroid of the shaded area, let's say it's this one. And so that means that Y bar is now this. Okay? Of course. So again, it's not hard, but it takes many steps. And all these steps are very prone to errors, as you might imagine. Let me check the chat. Why is TF the vertical thickness of the fan, not the horizontal thickness? Lowercase t, there's always a... No, this is just the way, Mahmoud, this is just the way I labeled them. These are just numbers. I call them TF because I know it's the thickness of the flange, and TW because it's the thickness of the web. So it doesn't have anything to do with conventions or formulae. Okay, does this make sense? All good? All good. Let's demonstrate that the shear stress must always start at 0 and end at 0 at the top and bottom fibers of the section. Okay, so if I take this one, if I take this fiber and I want to calculate the stress here, let's call this point B. What is the shear stress at B? 0. Why? What is the shaded area? If I shade the top area, how much is that area? Well, we are already at the top of the section, so of course the shaded area is 0. Wait a minute then. But Arnaldo, you told me that I could choose the top area or the bottom area. So yeah, the top area is 0. So what happens if I choose the bottom area? Well, the bottom area is the entire thing. Well, let's look at Y bar. Y bar is the distance between the centroid and the centroid of the shaded area. But the shaded area is the area, is the entire area. So the distance between the centroid and itself is 0. So it doesn't matter if you choose the top area or the bottom area. The stress is always 0 because Q is 0. This Q, if you take a point at the top or a point at the bottom, is always 0. So it doesn't matter V, I, T, they are just numbers. The Q becomes 0. And how do we know that Q is the largest at the centroid? Because of course that Y bar is continuously increasing as you scroll down from B downward. But then once you overtake point C, the centroid, once you overtake that centroid, that Y bar starts decreasing. That's the idea. Okay, test it for yourselves, but even easier if you take a rectangular section. If you do this on a rectangular section and you leave all labels, no numbers, you do it for a rectangular section, you find out that you get y squared. That is exactly the parabola. So tau depends on y squared. Any questions on this? No? Yes.
Yeah, Is the centroidal line the neutral axis?
The centroidal line, yes. The centroidal line is also the neutral axis, but the neutral axis is in bending. So if you consider bending, the centroidal line is the neutral axis. But of course, this is direct shear, so we don't need the neutral axis for anything. Yes?
You said for like I-beams, they're called in like construction and stuff, for shear, still want a really small web.
Yeah.
Is that to minimize that section there?
Well, no, that doesn't depend on how large it is. See, the thickness, if you make it small,
It's going to have a less.
no, it's going to have a larger stress. The problem is that shear stress is not very, it's not a problem. This is only 64 megapascal.
Yeah.
Whereas as normal stress in bending, you can easily get hundreds of megapascals.
So moments make it more.
Yeah. The moment generally for slender beams, which are longer than thick, longer than they are thick, the bending moment is always king, basically. Okay. Now this one it's a particularly thin beam, and you also don't want this flange to buckle, this web to buckle. So depending on how it's loaded. Okay. Now buckling is one of the topics that you will do this year in 206 in 5035 MA. Okay. All right, so let's do torsion. Torsion is very similar to bending, and I mean extremely similar to bending, but instead of happening outside of the plane, because bending happens outside of the section. So this is the section in 3D, this is the area. Bending happens here. Okay, so if this side goes one way and this side goes the other way, you are bending this beam. All right. Torsion, instead of happening outside of the section, the stress happens inside the section. As I'm saying here, it's much easier to draw because everything is 2D. You see, you have that this T, which is the twisting torque, is being distributed over the area in a linear way, exactly like the bending stress. But we are talking about shear stress because it's in plane rather than out of plane. And every point has its own associated tau. And tau is 0 at the center and grows larger and larger the farther away you are from the center. Okay, so if I take any point, say I take point B, if point B is here, the stress associated with this point is I take the radius, and this arrow is proportional to the radius. It's perpendicular to the radius and proportional to the radius. So the larger the radius, the larger the arrow, in the direction of the torque. So since this torque is clockwise, that means that this tau xy at B is going in this direction, perpendicular to the radius, always. And so this is very simple. If I write the equation for the bending moment, for the bending stress, sigma, remember, is m over I times y. Is it exactly the same thing? Huh? It is exactly the same thing. Okay, m is t, I is j, and y is r. And so in fact, they have the same distribution. It's a linear distribution exactly as it was for the bending stress. See, this is the bending stress. It's a linear distribution. You have exactly the same linear distribution for twisting torque. But of course, in this case, it's symmetric because the section is a circle. So you don't have any skewness. What is this J? What is this J? It's called polar moment of area. Polar moment of area. See, it's here. And again, it's another integral. It's the integral of r squared dA, where it's the radial distance between a point and the point of interest over the entire area. Again, you have tables that give you these. Now, J for circles, for circular sections, J is pi d to the power of 4 divided by 32. So depending on the diameter. What happens if you have a hollow section? It's a circular section that is hollow. It's the same if you take the larger circle minus the smaller circle. So it's pi larger d to the power of 4 divided by 32 minus pi times smaller d to the power of 4 divided by 32. Okay? No issues. What is the angle of twist? Well, the angle of twist is the deformation associated with torsion. Of course, if I twist something, if I apply a torque to something, that something will get twisted by a certain amount. How much is the amount? Depends on how much I am twisting, of course. It depends on how stiff is the material. This is called shear modulus, remember. And what are the properties of the section, so J. So say the larger is the section, the larger is J, and so the less it will twist. And of course, it depends on the length. Now, this is the general formula, which you should integrate. So if t is changing with x, or g is changing with x, or j is changing with x, you have to use the integral. If t is constant, g is constant, j is constant, they go outside of the integral, and this is just. If everything is constant, TL over GJ, that's what you need. We are going to assume everything is constant so far. Later on, we might change what happens. All right, so the diameter of a shaft is 20 centimeters. Let me say that this diameter, D, is 0.2, let's call it 200 millimeters. Let's call it capital D. Find the safe maximum torque which can be transmitted by the shaft if the permissible shear stress in the shaft must be 4,000 newtons per centimeter squared. Well, since everything looks to be in centimeters, let's take this as centimeters as well. It's a very odd unit to use. Engineers don't like to use centimeters. We like meters or millimeters. Because always 10 to the power of 3, 10 to the power of 6, 10 to the power of minus 3, minus 6, nothing in between. But since everything looks to be in centimeters, let's use Newton and centimeters. Now, the maximum stress, maximum shear stress is 4,000 Newton per centimeter squared. And the maximum angle of twist must be 0.2 degrees per meter length. Okay? Degree per meter. G is, so the shear modulus is 8 million newtons per centimeter squared. And given that the shaft rotates, so omega of the shaft is 320 RPMs, what is the maximum power? So we want to find the torque, T max, and power max. Let's call this rate of power. Let's call it W dot max. This is what we want to find. Well, we have all the information we need. We know that tau is T over G, so T over J times R, where R is the distance from the center. Now, tau max, of course, the torque is constant. J is constant, given it's a geometrical property. So what is tau max? Tau max will happen all around the circumference, all around the edge, because that's where the radius is maximum. So I can say that tau max is R max. But R max is the diameter divided by 2. Do you agree? So I can rewrite this by saying that tau max is the torque, the maximum torque, divided by, what is J? It's pi d to the power of 4 divided by 32 times the diameter divided by 2. Agreed? So I can simplify this, and this becomes the power of 3. And so T max, that means that T max is this 32 becomes 16. So this T max is tau max times P times pi. So tau max times pi times d cubed divided by 16. You agree with me? Did I make any mistake? Looks good to me. So pi is a number, the diameter is a number, tau max is a number, 16 is a number, it's just 16. So we do this. This should be equal to 4,000, so pi times 20 to the power of 3 times 4,000. These are all centimeters, see? Divided by 16. This gives me 43.9 kilonewton meters. Do you agree? Of course, you get this in centimeters. You get this in Newton centimeters, which you can turn into kilonewton meters. Can you please check if this is correct? It should be. And finally, the power. What is the equation of power? Power equation? Torque times angular speed. Okay, so we have the maximum power is just maximum torque times omega. So maximum torque is a number, it's 43.9, 43,900 Newton meters, times 320 divided by 60 radians per, sorry, this is times 2 pi divided by 60 radians per second. This gives 1.7 megawatts, 1.47, 47. That's quite a large amount of power. Okay. All right. See, this is very easy. You don't need too much. Now, I am not going to solve this one, but I'm going to sketch the solution of this question 9. Question 9 say, a solid circular shaft is to transmit a power of 160 kilowatts at 180 RPM. What will be the suitable diameter of this shaft? Oh, sorry, did we miss something here? Oh, we also said that the permissible angle of twist is 0.2 degrees. So this is not the end of the story. We found the tau max, we found T max given tau max. We can also find T max given the other one. So let me not solve question 9, because I want to finish this one. So this is one condition. This is condition 1, maximum stress. We also have the maximum torque for condition 2, max angle. What is the angle of twist? TL over GJ. So we know that phi max is phi max over L, because this is what we want. It's degrees per meter length. It's T over GJ. And so we can say that T max for condition 2 is phi max over L times GJ times G times pi d to the power of 4 divided by 32. So you find T max for condition 1, which I believe is larger than this. How much is this? You have to transform this So phi max, this is phi max over L, which is 0.2 degrees per meter. Okay, so this is phi max over L. But it's per meters. So you should turn this into degrees per centimeters, which is divided by 100. Okay. So if you do this, is 0.2 divided by 100 times 8 million times pi times 20 to the power of 4 divided by 32. How much is this? To the power of 4. Yeah. You get a larger value, basically. And then of these two, you have to take the smallest one. Because if you take the largest one condition is satisfied, the other is not. If you take the smallest one, both conditions are satisfied. Yeah? Is it? Is it larger than 43.9 kilonewton meters? Come on, we have to go.
I got something very large.
Yeah, we do.
2513 kilonewton per meter.
2513. Okay.
2513.
Of course, this one is not good enough. This one, no. Why no? Because if we allow for this much, then the shear stress will be too large. Okay, so this is the condition on the shear stress. You get the maximum torque is this. The condition on the twisting angle, the maximum torque is this. And of course, what you want to use is this maximum torque, because this satisfies both, and this one satisfies only the second one. All right, this one is very easy. So it's basically more of the same. It's exactly the same as we did, but there are different unknowns, but they're the same equations. Okay, so try to do this yourselves. This is a design question where the unknown is the diameter. So you want to transmit a certain power at a certain speed, and you have a certain maximum stress because you know the material. So how large must be the shaft? That's how you do it. Just the same question, but the unknown is the diameter. Thank you very much. I'm going to stop recording now.